I don't see any record option. Um, Let me just record the screens. I think it will record automatically. I'm guessing. Okay. Reward said it is recording it. Okay, great. Uh, so, sorry about the delay. Welcome to the Microeconomic Theory II course on the 26th of March. Um, so the topic that we'll cover today is so far we have been talking about simultaneous move games. So basically meaning games where players move simultaneously, player choose strategies simultaneously. So we will start a new topic where we will talk about dynamic games or sequential move games. Okay, so in these kind of games, players move in sequence. So think about the Stackelberg model that we have done in our class. So in that model, there are two firms in the duopoly case, and there is a leader and there is a follower. So first, the leader decides how much to produce. So that's the strategy of the leader firm, and then the follower firm observes leader's choice of strategy and then chooses its own level of production, its own strategy, right? So this is a game theoretic context where players move sequentially, and the player that moves second can observe the choice of the first player. Okay, so these are basically contexts that now we will analyze. So basically, in short, dynamic games are games where players move sequentially. Okay. Um, so we will start with a simple example, and we'll highlight the various conceptual details related to sequential move games, and then we'll move to other examples. So the first example that we're going to talk about is a context where there is a firm already present in the market. So think about that firm as the current monopolist. So we'll refer to that as the incumbent firm. Okay, and then there is another firm that is considering whether to enter the market or not. So it's a new firm. It's a potential entrant. Okay, so there is a potential entrant firm. There is a potential uh, entrant firm. We'll refer to this firm as firm 1 and an incumbent firm, which we'll refer to as firm 2. Now, what is the sequence in which the two firms move? So first, the potential entrant decides whether to enter the market or not. Okay, so first, F1 decides whether to enter the market or not. So that's the two possible strategies of the entrant, potential entrant. If F1 decides to enter, then 2, the incumbent, the current monopolist, the incumbent firm decides whether to accommodate the entrant, whether to accommodate the entrant, or engage in a price war with that firm. So, but this choice is only relevant when firm 1 decides to enter. If firm 1 decides not to enter, then the game ends there. Okay. So if the firm F1 enters, then F2 decides whether to accommodate the entrant, meaning that whether to sort of behave cooperatively with the firm, or be very aggressive with the firm. So that means going on a price war with the firm. Okay. So these are the two strategies of F2. So what are the payoffs? Uh, what are the payoffs? If one stays out, so we'll call it strategy O, then the payoff is 0 4, 0 for firm 1 and 4 for firm 2. Okay, that the game enters right then if firm 1 stays out. However, if one comes in, we'll refer to as I, and if 2 accommodates, then the payoff is 2 2. Okay, they share the payoff. And if F1 comes in and F2 engages in price war, then payoff is -1 -1. Both firms lose. Okay, so that's the payoff. Okay. Now, so this is the description of the game. These are the players. That's how I have mentioned the sequence of moves and the strategies. Okay, and the payoffs. Now we can express this game in the normal form expression, which is the matrix form, and then study what are the Nash equilibrium, and then we will sort of discuss what are the issues with that. Okay, so let's first write down the let's first write down the normal form expression of this game. So the payoff, the matrix format. So we'll write F2 on top. So F2 has option to either accommodate or engages in price war. And options for F1 is whether to enter or not. So I means in. Now, in this case, the payoff is 2 2. In this case, payoff is -1 -1. If firm 1 stays out, then firm 2's strategy is irrelevant. So the payoff is 0 4 0 4 in both cases. Now, let me just highlight one fact here. Here, notice that firm 2's strategy A or P is only relevant when firm 1 enters the market. However, for the game to be analyzed, i.e. for especially for firm 1 to make a decision or to evaluate whether to enter or not, firm 2 must have a strategy in case firm 1 enters, right? So the strategy of A and P, even though it is irrelevant when firm 1 stays out, uh, before firm 1 decides whether to enter or not, firm 2 ideally should have a plan. So firm 2 should have a strategy about what to do in case firm 1 enters. Without such a strategy specification, i.e. the plan of action in case firm 2 gets to move. Firm 1 doesn't know whether to enter or not, because for firm 1 to decide whether to enter or not, it must know what firm 2 might do, right? And in that case, that's why I've you can write down a 2 by 2 matrix format, normal form expression again, right? So here A means the strategy that firm 2 will choose in case firm 1 enters is accommodate, and P means the strategy that firm 2 will go for on a price war with the firm 1 in case firm 1 enters, right? So it's a plan of action. So given this, we can think about, we can try to find out Nash equilibrium of this game. Let's consider the first case. So suppose firm 1 decides to enter. What is the best response for firm 2? It's to accommodate, right? Because if firm 1 enters, firm 2 gets 2 from A and minus 1 from B. Now, if firm 2 has a plan of action to accommodate in case firm 1 enters, what would the best thing for firm 1 to do? Uh, it's again to enter the market, because knowing that the firm 2 would accommodate in case of entry, firm 1 would like to enter and get payoff 2 rather than stay out and get 0, right? So the first Nash equilibrium that we get is this. So let me just write here. So I comma A is a Nash equilibrium of this game. Okay. Now it turns out that there is another Nash equilibrium. So consider this. So suppose firm 2 threatens that it will go on a price war with the firm, with the entrant, in case the potential entrant enters the market. Okay. So suppose firm 2's plan is to choose P. Given that firm 2 chooses P, firm 1 would actually like to stay out, right, and get 0. And given that firm 1 is staying out, firm 2 doesn't have, is indifferent between accommodate and price war, because both cases firm 2 gets payoff 4. So choosing price war is a best response. Okay. So then we have another mutual best response, and hence another Nash equilibrium, and it is this object. So it turns out that staying out and price war is also a Nash equilibrium. Now let's talk about this specific Nash equilibrium. So how the way this Nash equilibrium works is that, basically, intuitively speaking, is that firm 2 is threatening to go on a price war in case firm 1 decides to enter, and given that threat, firm 1 decides to stay out. Okay. Now we know that it is a sequential move game, right? So first firm 1 decides, and then firm 2 decides its own strategy. Now the question to ask is this Nash equilibrium a intuitive way of thinking, or the right way of thinking what the way the firms will actually behave in reality? So imagine, so the question to ask is, the threat that firm 2 is giving to firm 1, is this threat credible? What do I mean by credible? Will the incumbent firm actually go on a price war, so sort of follow through on the threat, in case firm 1 decides to enter? So suppose firm 2 says, I'll go on a price war in case firm 1 enters. Now, knowing that, of course, firm 1's best response is to stay out, but suppose firm 1 decides to enter, makes a mistake and decides to enter, what would firm do? Would it follow through on the promise, on the threat? And the answer is no, right? Because firm 2 can see that the firm 1 has entered. It's a sequential move game, and firm 2, knowing that firm 1 has entered, knows very clearly that firm 2 is in this part of the game, in which case firm 2 would better choose A rather than P, right? So in case firm 1 enters, firm 2 has no incentive to follow through on the threat. okay, and would rather prefer to accommodate. So this Nash equilibrium involves a threat on the part of the second mover, which is not credible. So this Nash equilibrium involves a threat strategy of F2 which is not credible. Okay, which means that basically that if firm 1 enters, firm 2 actually not choose B, right? It would choose A instead. Now, given that we know this, we sort of understand that this concept of Nash equilibrium um, may not always give us the sort of the right set of strategies, pair of strategies as equilibrium strategies in games that are sequential move games. Okay, so even though OP is a Nash equilibrium, OP doesn't sound like something that will actually happen in case this is played in reality. Okay, so the question is, how do we kind of rule out certain Nash equilibria and pick the quote unquote right Nash equilibrium from the set of all Nash equilibria in sequential move games. Okay, so that's the new thing that we have to think about. Now, in order to sort of pick the quote unquote right Nash equilibrium, we have to change the way we express the game, right? So right now, this is the normal form expression, normal form expression. Right now, we move to a different format. We'll move away from the matrix format, and that's the new thing that will help us pick the right equilibrium. So this new format of expressing a game is called extensive form expression. This is basically a tree form. What do I mean by tree form? It has nodes and branches or arms. So we'll start with a node. A node will refer to a position of a player where the player gets to move. So we know that first F1 moves, right? So we'll say that there is a node with player F1 sitting there, and it's deciding whether to stay out or come in. So there are two possible strategies, and each strategy is referred by an arm coming out of the node. Okay, so this is out and this is in. Okay, if firm 1 stays out, then the game ends, right? And the payoff is 0-4. So we write the payoff at the end of each arm if there is no other move after that arm. So if the game ends after that arm. But if the firm 1 stays comes in, then firm 2 comes into the picture. So then firm 2 decides. So now there is another node, which is firm 2, and firm 2 decides whether to accommodate or go on a price war. So I'll write A for accommodate, and P for price war, right? And then again the game ends. Now, in case the firm accommodates after staying in, then the payoff is 2 comma 2. In this case, it's -1 comma -1. So this is an extensive form expression of the same game. Okay, so the previous matrix form was normal form. This is extensive form. Okay, and this tells you how the game actually proceeds in sequence. From the matrix form, you do not see the sequence of moves. That's not visible in a matrix format in the normal form expression. But in the extensive form, because we have this tree format, you see the sequence of moves. Who moves first? What are the possible actions? So you see the entire sort of sequence of the play. Okay. Now, given this extensive form expression of the same game, we will apply a concept to solve the game, which is called backward induction. Backward induction. What is this idea of backward induction? We will start with the last nodes where a players move. Okay, so we'll start with the last nodes of the game, the last time any player gets to move. So we begin with the last nodes of the game. In that node, a player is moving. So we will decide the optimal best thing for that player to do in that node if the player could choose its strategy on that node. Okay. So suppose the player is sitting at the last node, whichever player is there. If it could decide where to move, which branch, which arm to choose, which one would it choose? Okay. So and we'll treat that as the action that will be chosen by the player sitting on the last node. Given that choice, we will go back. We'll go back to the previous node and we'll again do the same thing. We'll decide what that player sitting at that second last node will do, knowing that going forward the guy at the last node will choose optimally. Okay, so we'll go backwards like that, and hence the term backward induction. So how would it play out in this game? So consider first player 2, f2, sitting on this node. So this is the terminal. So this last node is called the terminal node. Okay. So f2 is sitting on this terminal node. So if firm2 could decide sitting on this node which action would be optimal for itself, it would definitely choose A, because A gives pay of 2 as opposed to -1 from B. So firm2, if it could move here, would choose A. Okay. So this is everybody knows. Both firms know that if firm 2 could move there on the last node, it would choose A. Knowing that, let's go back to the previous node where F1 is moving. So let's come to this node. So now in this node, firm 1 has an option to choose either out or in. It knows that if it chooses in, firm 2 on the last node would choose A, because that we have already solved. Okay, so we are going back. So we take firm 2's choice as given and then find out what would firm 1 do. If firm 1 stays out, it will get 0. If firm 2 goes in, then it knows that on the last period, firm 2 would choose A, and in which case it would get 2. Okay. So knowing that, firm 1 would go in, right? So firm 1 would go in knowing that firm 2 would choose A. And that it knows because we are both applying, both firms apply backward induction logic, that in the last period we find out what the last node player will do, and then we go back accordingly. Okay. So this backward induction logic tells us that I comma A would be played in equilibrium. So this we get to know by applying the logic of backward induction on the extensive form expression of the game. So now you can later show that this way of picking the equilibrium play will always pick a Nash equilibrium of the game. So we already know IA is a Nash equilibrium, right? From this analysis, we already know that IA is a Nash equilibrium. This analysis says that IA is a Nash equilibrium which satisfies the backward induction logic. Okay, so this is in some sense the quote unquote right or better or more appropriate Nash equilibrium in this context of sequential move games. Okay, so we say that so basically backward induction allows us to um, pick the appropriate Nash equilibrium of a sequential move game. Okay. Um, this subset of Nash equilibria which sort of satisfy backward induction. So IA is a subset of the set of Nash equilibria of the game that we have analyzed. So this has two Nash equilibria, IA and OP. So IA is a subset. So this subset of Nash equilibria that satisfies backward induction will refer to as subgame perfect Nash equilibrium. Okay, so these equilibria that satisfy backward induction are referred to as subgame perfect Nash equilibrium, or SPNE in short. The definition of subgame perfect Nash equilibrium is a bit broader. It accommodates games where you also cannot apply backward induction. So I am sort of I'll cover those cases later, and I'll give you the proper definition of SPNE in that case. But for now, let's just focus on cases where you can apply backward induction, and in those cases, in those extensive form games, the Nash equilibria that you get by applying backward induction will refer to as the subgame perfect Nash equilibrium. Okay, so for now let's stick to this definition, and I'll expand on that later. I'll cover cases where you can't apply backward induction. Okay, so I'll not do any proof to show that this logic of backward induction always speaks Nash equilibrium. You just take it as given that it will always be true. If you apply backward induction, it will always speak a Nash equilibrium. It's not obvious, but it will be the case. I mean, you can see how it will be a mutual based response. So it's sort of in this simple game, it's relatively easy to see. So now let's apply this backward induction logic in a bit more, a slightly more complicated game, not super complicated. So let me then draw another sequential move game. So this is example number 2. So first, player 1 moves. Player 1 has an option to either immediately go out of the game and end the game right away, or stay in the game. So I means in. If the player 1 chooses O, stays out, then the game ends right away. And payoff is 2-2 for the two players, 1 and 2. If it stays in, then player 2 moves, and it again has a strategy to stay out or stay in. If it stays out, then the payoff is the game ends right away. The game ends then. And if it stays in, then player 1 gets to move again. So player 1 moves again if 2 stays in. And it again has a pair of strategies, out or in. If it's out, then the payoff is 3-4. If it stays in, then the game also ends, and the payoff is 4-2. Okay, so this is the nature of the game. First one moves, it can end the game right away or continue the game. If it continues, two gets to choose to end the game or keep the game going. And if two chooses to keep the game going, then one again comes back and chooses the same strategies. Okay, so this is the sequence of moves. Now let's apply backward induction. Okay, so suppose, what is the last, so it has only one terminal node, so this is the terminal node where one moves. So what would one do in this terminal node? Clearly, if one chooses in, it gets 4. If one chooses out, it gets 3. Okay, so the best thing for one is to choose to stay in. So if one gets to move on the last node, it would choose to I. Okay, now knowing that, let's go back and go to the previous node. So this is the previous node where 2 is moving. So in this node, what would 2 do? If 2 stays out, it gets 3. If 2 stays in, 2 knows that 1 would also stay in which case 2 would get payoff 2. Okay, so since 3 is bigger than 2, 2 would actually choose to stay out. Okay, now let's again move one step behind, move to the first node where one gets to move. What are the possible strategies? So if one chooses to stay out, one would get payoff 2. If one stays in, one knows that 2 would optimally choose to stay out, in which case one would actually get payoff 1, right? So one would stay out. So how would the game evolve? If you see the game being played by two rational individuals, you will see that one would stay out and the game would end immediately, right? But what are the strategies that result in this play? The strategies are that when in the first node, one strategy is to move out, this one, and in the third node where one would move again, if one could possibly move, one would have chosen I, and two strategies to stay out when it gets a chance to move. Okay, now the outcome or the equilibrium play selects this as the payoff, equilibrium payoff. But if I have to write down strategies, what would I write? The strategies for player one in this particular game, notice that one moves twice. One strategy is to stay out in the first node and to stay in the second node. So notice I have mentioned two things about one's strategy. So this is player one's. So this is one's strategy. What does the two elements in the strategy mean? The first element refers to the plan of action in the first node. The second element refers to the plan of action the second time one gets to move, which is in the third node, okay, in the terminal node. And two strategy is O, is to stay out every time it gets a chance to move, right? So this we say is a Nash equilibrium that satisfies backward induction, and hence is a subgame perfect Nash equilibrium of the game. Okay. Now this idea of strategies in a sequential move game is a bit different than the idea of strategies in a simultaneous move game. Here, the word strategy in a sequential move game refers to a plan of action in all possible nodes where a particular player moves. Okay, so notice that if one has a strategy of staying out, if one has a strategy of staying out in the first node, one knows that it will not move in the third node, correct? However, for a strategy to be fully specified, it must say what it would do in this third node as well. So not only it has to specify something on the first node, but it also has to specify something on the third node, even if it knows that the third node may never be reached. The idea is that for a player one to evaluate what is to be done on the first node, it must have a full plan of action, what it would do if it could move on the third node. In absence of such a full plan of action, it is not possible for player one to decide what to do on the first node, right? So that's why the idea of strategy here refers to a plan of action, meaning the choice of action in all possible nodes in which that player moves in the game. Okay, so let me write it down. I think it bears emphasis. So strategies in sequential move games refer to a plan of action, i.e., it specifies actions to be taken in all possible, so not possible, in all nodes where the player can move. So it specifies an action in all nodes where a player can move, okay, even if that node is never reached in the actual play of the game. So that's what a strategy means. So let's go back to this game. So what are the possible strategies of player one? Player one could choose O in the first node and I in the second node, right? So that's an equilibrium strategy. But player one could have chosen O in the first node and O in the third node as well, correct? The plan that could be that's a possible plan of action, even though that's not a very good plan of action. That's not the optimal plan of action, but that's a possible plan of action. So as you can see, it's sort of all permutation combinations of these possible actions. So O is a plan of action. OI is another plan of action. IO is a plan of action, meaning I in the first node, O in the third node, and II. So always stay in whenever it gets a chance to move. So that's the set of strategies for player one. Okay. This is different from actions, which I mentioned in the definition of strategy. Actions are basically the arms. Each arm is an action. So action for player one is just either in or out in every node. In every node, the action set is either in or out. But the strategies is for the entire game. For the entire game, the strategy specifies the full plan of action, and that's how the strategies are written. So you see, for player one, the set of strategies is different from the set of actions. Notice when if you remember, when I introduced this notation of A1, AI, and SI in the game theory, one of the first lectures on game theory, I mentioned that for the time being, we were assuming that set of strategies and set of actions to be same. I mean, we'd be using strategies and actions interchangeably. But now this is a time to make a distinction between these two things. So in a sequential move games, actions refer to the each arm, basically each choice of each choice in every node. So each choice is referred to an action. Okay. In this case, either it's in or out in every node. Okay. So that's the action set. It's this object. But strategy is for the entire game where you specify an action for all possible nodes where you can move. And so that gives you a different object. So it gives you these items like these. So in this sequential moves games, we see that a set of actions and set of strategies are different. For player two, because player two only moves once, player two's strategy is either to move in or out, which is also its action set. So for player two, the action set and strategy set are same, but for player one they're different. So that's why we make a distinction between, we use these two terms, strategy and action, in game theory to make a distinction between the two in the sequential move games. Okay. So this I wanted to sort of emphasize. Now, given that we have this set of strategies for both players, so we have this set of strategies for player one and set of strategies for player two, um, we can actually see what is the Nash equilibrium of this game. Okay, so let's try to see the Nash equilibrium of this game. So we can let's write down the game using the normal form expression, right? So because that will be easier for us to identify the Nash equilibrium of the game using the normal form expression. So let me write down a 4 cross 2 matrix, right? So so for player one, the strategies are sorry, in out, in out, out in. And for player two, it's either in or out. That's for player two and player one. If player one stays in, and player two also stays in, and then player one stays out, let me just look at the game. Both stay in and player two stays out, so it's 3-4. If player two stays out, then it's 1-3. If they all stay in all the time, then it's 4-2. If player two stays out, then it's 1-3. If player one stays out in the first node, so here in both cases, player one stays out of the first node, so player one ends the game right away. So it doesn't matter what two strategy is. So the payoffs are always 2-2-2-2-2-2-2. Okay. Let me just check whether our subgame perfect Nash equilibrium is indeed a Nash equilibrium or not. So what is our identified SPNE? We identified this as our SPNE. OI, O. Let's check whether OI, O is a Nash equilibrium or not. What is OI? So OI is here. So suppose 2 chooses O, then one has two best responses, OO and OI. So OI is one of the best responses. And if one chooses OI, then 2 is indifferent between in or out, and therefore out is a best response. So this indeed is a Nash equilibrium, OI, O. But there are, as you can see, there are several other Nash equilibria. So this is a Nash equilibrium as well, for example. If 2 chooses O, one could choose OO as a best response, and if one chooses O, 2 choose O, right? Are there any other Nash equilibria of this game? Let's check. If 2 chooses I, then II is a Nash equilibrium. Sorry, II is the best response, and if II is chosen by 1, um, then O is chosen. So no. So it's basically, so the game has no other Nash, no other Nash equilibria. So the game has two Nash equilibria. So the game has two Nash equilibria. They are OO, comma O and OI, comma O, and of them OI, comma O satisfies backward induction, and this we know because of the analysis we did here. Okay, so you see that the backward induction logic picks an equilibrium strategy which is indeed a Nash equilibrium in this example at least, and that will be true in all examples. Okay, but it also filters out some Nash equilibrium. It doesn't choose OO for comma O, for example. So this is sort of equivalent to an inappropriate Nash equilibrium in this case. Okay. Um, let's solve another one, a bit more complicated stuff. I mean, not that complicated, but yeah, marginally more. Um, so first one moves. It can go either up or down. If one chooses up, two moves after up, and two's possible actions are A or B, after which the game ends. The payoffs are 1, 4 and 5, 2. If one chooses down, two moves again, and two has strategies C and D. Two has actions, sorry, C and D. If 2 chooses D, then the game ends. Payoffs are 6, 2. If 2 chooses C, 1 moves again. And one strategies, sorry, actions are E, F. And payoffs are 3, 3 and 2, 0. Okay. Um, Now, so this is the full game. Let's identify. So let's use backward induction to solve this game. So this is the terminal node, one terminal node. There is another terminal node which is here. It's also the last node where a player moves, after which the game ends. So let's first look at the bottom terminal node where one moves. What is the best thing for one to do? What is the optimal thing for one to do? One would choose E, right? Because in which case it gets 3 as opposed to 2, right? Let's now move to the top terminal node. In the top terminal node, what would 2 do? 2 would choose A, right? Because 2 gets 4 from choosing A as opposed to choosing B. Now let's come down to the bottom terminal node. Let's go back. Let's move to the previous node here. In this node, 2 moves. If 2 chooses D, 2 would get payoff 2. If 2 chooses C, 2 knows that one would optimally choose E, in which case 2 would get 3, right? So it will get more. So 2 would choose C if 2 could move in the bottom node. In the top node, 2 already I've decided, we have analyzed that 2 choose A. Now let's come to the first node, the initial node. where one moves. If one moves up, then one eventually ends up getting one. If one moves down, then it knows the how the play of the game will proceed after that, and one would get three. So then optimally one decides to move down, right? So how the actual game will be played: one would move down, then two would move C, two would choose C, and one would choose E, and then if both players will get three each. Okay. So 3 comma 3 is the equilibrium payoff. But what is the strategy? How would I write down the strategy? So notice one moves twice in this game, in the initial node and in the terminal node. Two also moves twice, in the top node and in the bottom node. Okay. So for both players, I have to specify the full plan of action, meaning I have to specify actions for both nodes for player one, and I have to specify action for the top and the bottom nodes for player two. Okay. So what is the equilibrium strategy here? For player one plays D, uh, E, right? DE is is the strategy chosen by player one, meaning that it chooses D, action D in the first node, and if it has the option to move on the second time it gets to move on the terminal node, it would choose E. Okay. What is the strategy chosen by player two? So for player two, I'll write the top node first and the bottom node later. I mean, this ordering is not important as long as you specify what you are doing. So in I'm writing the top nodes action first and then the second bottom nodes action. So on the top node, two chooses A, and on the bottom node, two chooses C. So the strategy is AC. Sorry, AC. So this is a subgame perfect Nash equilibrium of the game. Why? Because it satisfies backward induction. Okay. Again, you can write down sort of the normal form expression of the game. It will be a 4 by 4 matrix, right? Because there are four possible combinations of actions for one. So say for one, it is D E D F U E U F. So these are the four possible combinations of choice, right, in this game. For player two, it is A C A D B C B D for player two, and this for player one. So you can write down this 4 by 4 matrix and evaluate that whether this cell is indeed a Nash equilibrium or not. Okay. Um, you can try this as part of an exercise at home. Okay. Um, so let me do one last case and then I'll stop. Um, so let me write down this third game. Um, First player one moves. Choices are A and B. Then player two moves. Choices are on the top C, D. on the bottom EF. For 1, again 1 moves after that. Choices are GH. Here again 1 moves. Choices are IJ. Here 1 moves. Choices are KL. Here again 1 moves. Choices are M, N. And the payoffs are 3,8, 7,9, 1,2, 2,1, 10,4, 0,5, 4,0, 8,3. Okay, so this is the entire game. Let's apply backward induction. There are 4 terminal nodes. Sorry, here also 1 moves. There are 4 terminal nodes. This, this. In each of the terminal nodes, the same player moves, player 1. So let's look at the top node. The top node, the best thing for 1 is to choose H, right? Because it gets 7 as opposed to 3. In the second, from the top, the best thing for 1 is to choose J because it gets 2 as opposed to 1. On the third one, the best thing for 1 is to choose K because it gets 10 as opposed to 0. And then at the bottommost, the best thing for 1 is to choose N because it gets 8 as opposed to 4. Okay. Let's move one step behind. So let's start with the top one. So this one, what would 2 do at the top node? 2, if chooses C, it will land up getting 9. If 2 chooses D, it will end up getting 1. Then it would choose C on the top node. What would it do in the bottom node? In the bottom node, if it chooses E, it will end up getting 4. If it chooses F, it will end up getting 3. So it will choose E. Okay. And knowing this, what would 1 do at the very beginning, the first node? If 1 chooses A, it will end up getting 7. If 1 chooses B, it will end up getting 10. So 1 would choose B. Right? Yeah. So then, so this gives you the Nash, subgame perfect Nash equilibrium. What will happen in this? The actual move will be 1 would choose B, after which 2 would choose E, and 1 would choose K, and then the game will end with this being the equilibrium payoff. The question is, what is the equilibrium strategy? The equilibrium strategy, again, so now equilibrium strategy is here, 1 has how many nodes to move? In the beginning, 1, and then 4 terminal nodes. So 1 has 5 places to move. So 1 has to specify an action for each of the nodes. Okay. So 1 has to specify 5 things that in aggregate will give 1 strategy. So the equilibrium strategy here, I'll start with the first node. So equilibrium strategy is to choose B in the first node, and I'll then in sequence write the 4 actions from of the 4 nodes, 4 terminal nodes starting from the top. So on the top, it likes to choose H. The second one, it likes to choose J, then K, and then N. So this is the strategy that 1 is choosing in this play in equilibrium. B, H, J, K, N, the 5 elements. What is the strategy for 2? 2 has 2 positions to move, here and here. So it specifies two things. So in equilibrium, it is choosing C on the top node and E on the bottom node. So this is a sub-game perfect Nash equilibrium of the game. I'll not ask you to check whether this is a Nash equilibrium of the game using normal form, because it will be a humongous matrix. So don't worry about it. But if you could do, you could see, you could actually check that this indeed is a Nash equilibrium of the game. If you could write down the humongous matrix. Okay. So let me stop here. So this sort of, basically today we have discussed extensive form expression, which is applicable, which we sort of use often for sequential move games. And this analysis of sequential move games using extensive form expressions help us to apply backward induction logic, which picks out Nash equilibria, which are sort of more intuitive, more appropriate, and we refer to them as subgame perfect Nash equilibrium. Okay, so let's stop here. In the next class, we will talk about cases where you cannot apply backward induction even in sequential move games, and how to sort of apply the concept of SPNA in such cases. Okay, so that's for the next class. Let me go back to here. Let me now ask you if you have any questions.
Yes, Professor. Could you explain the logic behind? I didn't really understand how you arrived with the Nash equilibrium for the first example, for the in and out example. How you arrived with the Nash equilibrium in the normal form, the 2-2.
This one, right?
Yeah. No, the next one. The next one.
Here.
Yeah. In the normal form.
So this is the normal form of that same game. Are you talking about this game or the next game?
No, I'm talking about the.
Oh, I see. You're
Yeah.
talking about this one.
Right? Yeah.
So for this game, so you write down these strategies in this matrix form, right?
Yeah.
And then check. So then once you have the matrix form, you can always apply, whether it's mutual based response to find out Nash equilibrium. So let's say, suppose one chooses OI. What is the best response of player 2? Player 2 is indifferent between choosing I or O, because both gives payoff 2. So O is A best response, right? So this is A best response. If 2 chooses O, then both OO and OI gives player 1 the highest payoff. So OI is A best response given player 2 is choosing O. So then you have a case of mutual best response, that when one chooses OI, 2's best response is O. If 2 chooses O, one of the best responses is OI, right? So then that ensures that this is a Nash equilibrium.
But Professor, what about IOI 3 and 4? So if
IOI, so yeah, so let's check that. So suppose one chooses IO, then 2's best response is I.
Yeah.
But if 2 chooses I, one would like to choose II, right? It's not, IO is not the best response if for player 1 if 2 chooses I.
Oh, okay.
Right? And if one chooses II, 2's best response is actually O. And if 2 chooses O, then one's best response is not II, is one of the bottom ones. Right? So at the top, you don't have any Nash equilibrium.
Okay. Okay, got it. Thank you.
Professor, I had a doubt about this last lecture.
The last, yeah. Let me move there.
Yeah.
Yeah, this one.
Um, so this was the last lecture when we were doing the court-imposed penalty.
Oh, the last lecture. Yeah, yeah. Tell me.
Yeah, in that won't Northwest also be an equilibrium scenario?
Uh, yes,
Minus
in the limited verifiability case.
verifiability. Okay.
Right.
But why is it just in the limited verifiability? Oh, right. Yeah. Okay.
Because so yeah, so it gets removed in the full verifiability case because
Right.
in the full verifiability case you are manipulating each sales payoff, right? You could manipulate in the contract. You can say that when one party doesn't invest, then that party pays the other party. So that if you check, that actually removes NN as a Nash equilibrium. But in the limited verifiability case, you can't have a cell by cell payoff manipulation in the contract because the court can't see each cell. So there, NN remains one of the Nash equilibria.
But also, Professor, in the last example,
Yeah,
the the strategy that we've written for player one, BHJKN, is it
right.
sequence of the nodes, like the first node, then the second node? What will is
Ha,
that
so yeah, so the sequencing, I mean, follow some kind of natural order, or you can also
okay?
specify when you write what is the order you are following.
Oh,
Um, so that will help sort of remove any confusion.
okay. Thank you.
Yeah. Any other questions?
Yeah, Professor, just one small question. So
Yeah.
game perfect Nash equilibriums are those that satisfy backward induction, and the rest of the Nash equilibrium that we get from the normal form are the ones that wouldn't be viable options um, in a sequential game.
Right. Right. So for these kind of games where you could apply backward induction, the Nash equilibria that satisfy backward induction are the SPNEs of the game. So that we sort of like them more because they satisfy backward induction, and backward induction we think is a powerful logic to understand how the game would be played. Right.
Okay, thank you.
So if there are no other questions, I'll request Vibhor to sort of maybe send me the recording so that I could upload um, on YouTube. Let me stop the presentation then.